All right, so the warm-up today is to find the reference angle for theta equals 572 degrees. Reference angle, what do we know about the reference angle from yesterday? It's the angle closest to the x-axis. And there's two characteristics that always we know about the reference angle. It is acute and positive. So it's a magnitude only. It's not a vector like this angle's a vector, bless you. So I need to figure out where this guy lands. He's bigger than one rotation, isn't he? But he's not so much bigger than one rotation that I need to do the dividing out 360 and cancel rotations method. All I got to do is just subtract 360 from it, I think, and I get 212. So what type of angle then do we call 212? Well, how is it related to 572? It's coterminal. Thank you, Wyatt. So I'm going to put subscript coterminal there. Okay? Or you can use the symbol 572 degrees is coterminal with 212 degrees. Okay? Now 212 degrees is between 0 and 360, so I can figure out where he lands. That's 90, that's 180. It's going to be somewhere in quadrant 3. Yes, yes? So that's where both 572 and 212 and all the infinitely many other coterminal angles land. Now I need to find this angle here in red. This angle here is going to be the reference angle. And you always work off the x-axis. So if this is 180 and this is 212, do I do 180 minus 212 or 212 minus 180? If I want it to be positive. 212 minus 180. I've gone past 180 by a certain amount. So now I just do minus 180 and I get 32 degrees. And there you go, folks. That's the reference angle. So tomorrow you'll have to find the coterminal angle between 0 and 360. So you would get a check for finding 212. You would get a check for drawing in the right quadrant, and you're going to get a check for finding the reference angle. So tomorrow you'll have more than just one question, of course, and I'll give you bigger angles, some that are negative. But this would be a 3-checker. Not bad, huh? Comments or questions on the warm-up? All right. Let me take a picture of this quickly and send it to my colleague who likes to use my warm-ups for her warm-ups as well, so that she makes sure her classmates are getting the same high-quality product that y'all are. She's using Korpi GPT. Core GPT. Core GPT. I don't know how you say that. Yeah, thank you. The KGP. Oh my gosh, that's something different. All right. So we've been using degrees and degrees minute seconds, okay? And that's one way to measure angle measure. But there's another way that's actually more prominent for people who deal with anything that involves distances or lengths, okay? Or really angle measure in general, okay? So today you're going to learn a very, very important definition. It's called a radian. It's called a radian. A radian is just another way to measure angle rotation. And of course, the key word in radian is what? Ian? Some guy named Ian invented this? Rad? Oh, yeah, rad is good. Yeah, this thing is going to be rad, like radical. What does this word kind of sound like? It sounds a lot like radius. Okay? And the reason it sounds a lot like radius is because, believe it or not, it's related to the radius. Right? So if you come off to the side here, if you take any circle in the whole wide world, any circle, okay, and you take the length of its radius, okay, if you center it at the origin, of course, you draw the coordinate plane, you center it at the origin, this is the radius. If you take that length of the radius and you wrap it around the perimeter, which is also known as the circumference of the circle, as soon as one radian length expires, okay, wherever that length of the radius expires laid out along the curved circumference, which would be right here, you draw a line back to the origin, and that angle that subtends the arc, we say, it creates an arc. S becomes an arc, okay? S is for arc length, in case you're wondering. S is for arc length, and if you're wondering why S for arc length, well, if you just sound out arc length very slowly, you can hear the S sound, right? Arcs, lengths, See, you hear that? Yeah, S is for stadia. It's the Greek unit of measure for the mile back in the day. So a stadium, they used the stadium for their measure. And so S comes from stadium, which is stadia, which is a length. So we use arc length for S. That's why. A was already taken for area. All right, so when you get this angle right here, that's acquired from wrapping one length of the radius around its circumference and drawing a line back to the origin, that theta is one radius, okay? One radian, okay? So theta is equal to one radian. Or, as we like to abbreviate, as Peyton already saw, we abbreviate it rad, one rad. Now, the question is, if we continue doing this, if we continue wrapping the length of the radius around the circumference, okay, this is another length of the radius. This is another length of the radius, one radius length. This angle here is 2 rads. If we draw this arc right here, we'll call that alpha. Alpha is equal to 2 radians. See that? So 2 radians is a little bit bigger than 90. Would you agree based on my picture? Yeah. 1 radian looks like it's maybe about 60 degrees. 2 radians looks like it might be around 120 degrees, somewhere in there. The question is, if I keep doing this, how many lengths of the radius can I wrap around any given circle? How do you know that? Can we fit exactly 6? This is another radius right here. So if you wrap another length of the radius here, you get 3 rads. So 3 rads is a little bit less than 180. 3 rads is a little bit less than 180, the way it looks, right? And if I continue this process, there's another approximate length of the radius. If I draw that angle back, this is 4 radians. If I do it again, right here, if I draw the line back, the angle that goes all the way around past 270, that would be 5 radians. If I draw another length of the radius, it takes me to about right there. That would be 6 radians. So for any given circle, irrespective of the size of the circle, the bigger the circle, the bigger the radius, right? Which is also the bigger the circumference. So this number is always the same. It just so happens that you can always fit 6 full lengths of the radius of any circle around its circumference plus a little bit more. What is 2 pi r?
So 2 times pi.
2 times pi times the radius gives you the what? That gives you the circumference, right? Does that tell you how many lengths of the radius you can wrap around? It's closely related. You're on the right track because you pulled out the equation for the circumference of a circle. 360 degrees is once all the way around. Well, 2 pi r is not 360 because it has r in it still. You just forget the r? I don't know. Let's think. It's related to that. It is related to that. You both are on the right track. So my question to you is how much more of the radius do we need to go to get back to 1 full rotation? Is it another length of the radius? Is it 7? No. Should it be closer to 6 or closer to 7? Yeah, it's just a little smidgen past 6. The question is, we don't know what that is just yet. But many of you are on the right track. Okay, so does everyone understand what a radian measure of an angle is? Okay, I went all the way around 1 radian, 2 radian, 3 and 4 and 5, and so 6 radians is a little bit less than 360. What we want to do is this. We want to figure out, and you're already kind of sniffing around on it. I want to know 1 rotation is 360 degrees, but I want to know how many radians it is. I want to know how many radians 1 rotation is. If I can figure out how many lengths of the radius I can wrap around the circle, I can now have a conversion between degrees and this other way to measure the angle, okay? So the way that we're going to do that is we're going to define what a radian measure of an angle is, okay? So here's the definition. The radian is the measure of a central angle of a circle subtended by an arc in length equal to 1 radius of the circle. The radian measure of the angle theta in standard position then, this is the most important part, It's the ratio of the arc length, which we're calling S, to the radius. It's the ratio of the arc length to the radius. Okay? This can be represented mathematically like this. So theta is equal to S divided by R, where S is the arc length and R is the radius of the circle, and we can write rads right there. So here's an example. Let's say the radius of a circle equals 5 feet. Okay? So let's come back up to this picture. Let's say that this R, I'll use green here. Let's say this R was equal to 5 feet. Okay? If I take that length and wrap it around the circumference here, one length is going to equal also 5 feet. Would you agree? So why is that equal to 1 radian? Well, theta, remember, is S over R. If the arc length is 5 feet and the radius is 5 feet, what's 5 divided by 5? You get 1. Now, here's what I want you to realize. What happens to the units of feet? They divide out, don't they? So what would the resulting units be? 1 nothing. The measure of the radian is theta equals 1 nothing. Not even 1 radian. 1 nothing. It's just 1. Okay? Because the radian is a ratio of two things that have the exact same units, the units will always divide out, which means the units of a radian are really what? Nothing. There is no unit measure of a radian. Now, because that can be confusing, if I just say the angle is 1, someone might say 1 what, right? 1 what? 1 degree, 1 foot. And you're like, no, 1 radian. It's unitless. We typically write rad after our angle measure. But you have to understand that when we write rad, it's only a what? Not a unit, but it's a description. It's not a unit. It's a description, not a unit. So if I ask you on the quiz tomorrow, what are the units of a radian? You should answer what? Nothing. If you answer anything else that affirms units, you're going to get it wrong. The radians are a unitless measure of rotation. Now, that's a very important aspect of a radian. In fact, it's kind of why we need radians. Because when we start applying our equations that we're going to derive to anything that involves length or distance, and we want to measure the rotation on the x-axis, we can't have degrees there because degrees are units and they're very, very specific and they will not work with the problem. The units will not match up. But if I can choose a unitless measure of rotation on the x-axis, now I can assign any units I want to the x-axis, like time in hours or distance in feet or whatever. I can assign units to the x-axis. That's very, very important. So what are the units of a radian? Nothing. They are nothing. We write rad as a description so people know we're talking about an angle measure. All right, now, what we need to do is figure out how many radians are in a full rotation. We need to figure out how many radians are in a full rotation. So let's do this. Let's say that the circumference, as Archimedes gave us, and some of y'all already hit on, the circumference of a circle is 2 pi r. Yes, yes? That's the formula that you all remember from geometry. Okay? If I go all the way around, I want to figure out what theta is for one rotation. So if I use the formula, theta equals S over R. This circle that I drew, which is not quite perfect, but you get the idea, has a radius of R. For one rotation, what's another name for the arc length if I go all the way around? No. What's another name for the arc length? An arc length is just a part of a rotation. It's part of the circumference, okay? I want you to realize that because that seems to be unclear. S equals arc length, which is just a piece of the circumference. The arc length is just a piece of the circumference. But for one rotation, What is the arc length? No. What's another name for the arc length if I, bless you, go all the way around? Y'all remember? It's too easy. If I go all the way around, the arc length for a full rotation is known as the what? Thank you. It was too easy. You were overthinking it. Okay? If I go all the way around for one rotation, the arc length is the circumference. So for one rotation, S equals C. Yes, yes? Okay. Now that only works for a full rotation. Now, if I substitute it in, I get S over R becomes C over R. Yes, yes? For one rotation. Again, I'm talking about all the way around. Now I can substitute Archimedes' formula in here. The circumference is 2 pi r, and I divide it by r. And as Lawson said earlier, just get rid of the r. Can we actually get rid of the r now? For a good reason, though, right? The radiuses, which have units of feet or miles or inches or whatever the distance unit is, not only do the r's divide out, but the units divide out as well with the r's. Would you agree? I hope so. If you like agreeing with something that's correct, you should agree. We get 2 pi. We get 2 pi. So there we have it. We just used Archimedes' formula to say that one rotation equals 360 degrees, which now equals 2 pi. And what should I write after 2 pi so that people know I'm talking about an angle? Rads. But when I put rads, is that a unit? No. It's just a what? It's just a description. Now, of course, 2 pi is approximately 6.28 dot, dot, dot. So, how many lengths of a radius can we get around any given circle? 6 full lengths plus a little bit less than a third of another. And if you want to hit the nail right on the head, you would say what? How many lengths of a radius can we fit around any circle? 2 pi of them. 2 pi of them. Okay? We now have this conversion factor. Okay? If 360 degree equals 2 pi radians, we can now say 360 degrees over 2 pi rads is a conversion factor. Yes, yes? Or the other way around, 2 pi rads is 360 degrees. How many degrees in a full rotation? 360. How many rads in a full rotation? 2 pi. Okay? Now, we can simplify that, can't we? 360 is an even number. 2 pi is an even number. So we could call that 180 degrees over pi rads. 180 degrees over pi rads. These become our conversion factors then, because they're the simplified version, for going back and forth between degrees, which are unit specific, to radians, which are unitless. Okay? So if I come back to this picture over here, I had 3 full lengths of the radius to get halfway. This is 180 degrees, we know that. How much was left over? 0.14159. Yes? Because that would be pi. 180 would also equal pi. So it's 3.14159. That's how much is left over there. In fact, we can kind of split this up now. 0 degrees is 0 radians. All the way around, 360 degrees is 2 pi radians. And if we half that, we can get this. We get pi equals 180. Let's half it again. What's half of 180? 90 degrees. That's straight up here on the y-axis. What's half of pi? How about just pi over 2? Are y'all okay with that? Pi halves? Instead of 0.5 pi or 1/2 times pi, we'll just call it pi halves. So what's another name for 90 degrees in radians? Pi halves radians. Pi halves radians is how many degrees? 90 degrees. Now, once we get to 90 degrees, we can count our other axes, can't we? 90 plus 90 is 180. 180 plus 180 is 270. 270 plus 180 is 360. I need to figure out how many radians 270 is, because that's straight down. So let's just count by pi halves. 1 pi halves is straight up. 2 pi halves is really pi, right? That's due west. What would the next one be straight down? 3 pi halves. 3 pi halves. And then the next one would be 4 pi halves, which simplifies to 2 pi. Yeah. These are very, very important for you to memorize, along with a bunch of others that are going to show up, because they're called quadrantal angles. Quadrantal angles. They define the quadrants. So we call them quadrantal angles. 0, 90, 180, 270, 360 now becomes 0, pi halves, pi, 3 pi halves, and all the way around, coterminal with 0 is 2 pi. Let's do it again. 0 rads, pi halves rads, pi rads, 3 pi halves rads, and 2 pi rads. Is it okay if I didn't write rads behind them? Yes, because rads are just a description. In fact, if I put 90 degrees equals pi halves, everybody knows that we're talking about radians there because it's in the context of an angle. So far, so good? Everyone know what a radian is, right? 1 radian is not equal to pi radians. 1 radian is about 57 degrees, okay? In fact, let's go ahead and do that before we get to example 7. We already did this. We did example 7. We just need the last part of it. Use the new conversion factor to determine the number of decimal degrees in 1 radian. So here's how we're going to use the conversion factor. 1 radian, 1 rad. Again, that's going to be this angle right here. That's the length of 1 radius along the circumference, which gives us the arc length, expanded out and drawn back. I'm going to convert that, okay? So I'm going to multiply by a conversion factor that's equivalent to 1. I want the radians to divide out, which is another reason we put rads there. It's nice to have something there to make sure the stoichiometry or the dimensional analysis works out. And what do I want to appear? Degrees. So what's the conversion factor? Degrees to radians. What is it? Can we put 360 to 2 pi? Would that be okay? Yeah, but what's the simplified version of that? 180 over pi. 180 over pi. 180 over pi. Now the radians divide out, and all we got to do is go to our calculator, Medora. Uh-oh, I lost it. I didn't. Criminy. Hang on. Yeah, it's just 180 divided by pi. But let me catch up so that we can do it on the. Okay, so it's 180 divided by pi. So I'll use the pi button on the calculator. I don't need to worry about times 1, do I? Because anything times 1 or divided by 1 is itself. What do I get? 57.295 if we truncate degrees. That's kind of a good measure to kind of know. 1 radian is about 57 degrees. It's a little bit less than 60 degrees. Okay? You know what else is good to know? Your quadrantal angles. Let's figure out how many radians pi halves is. What's pi divided by 2? It's about 1.570 rads. Okay? So if you want to go straight up to 90 degrees, it's going to take a little bit more than 1.5 lengths of the radius. Of course, we know what pi is, right? Pi is 3.141 if we truncate radians. Let's figure out what 3 pi halves is. What's 3 pi divided by 2? That's 4.712 rads. So if you want to rotate all the way to 270, which is 3 pi halves, it's going to take 4 plus another, almost the 5th one. Okay? And then, of course, we know 2 pi is what? 6.28. You get his 2 pi, 6.283. Okay? It's really more important for you to know pi halves pi, 3 pi halves, 2 pi, but it also is kind of nice to know that pi halves is about 1.57, and of course 1 radian, which doesn't make it quite up to pi halves, is what? What's the length of 1 radian about? Yeah, 57.29. Okay. Boy, that was a big day. That's a huge topic. If you get nothing else out of the second semester of pre-cal, you get the idea of a radian down. Because if you've done anything in your physics class or science class that involves rotation, You've probably already used the radian, right? Radians have just appeared, and maybe you didn't understand what a radian was. You're like, what is a radian? Why are we using radians instead of degrees? Okay? Now you know exactly what a radian is, and you also know the units of a radian, which are what? Non-existent. They don't exist. What's the unit of a radian? Nothing. There are no units. It's a unitless ratio of angle measure. Okay? And what is it a ratio of again? You got to know this definition. It's the ratio of what does that stand for? No. Arc length, right? Remember, if you say arc length slowly, you'll hear the S. Arc length. Hear it? S is from stadium, the unit of measure of the ancient Greeks, the stadia. That's where the word stadium comes from. Okay, and it's a length. So S is the arc length, R is the radius. So what is the definition of a radian? It's the ratio of what? Arc length to radius. Arc length to radius. Got it. Got it. Got it. All right, here are your two conversion factors simplified that we've already talked about. All right, now what we're going to do is we're going to convert. We've already done this, okay, but we're going to practice our conversion. You should already have this memorized. What is 90 degrees in radians exactly in terms of pi? It's pi halves. Let's verify. 90 degrees over 1. If I want to convert, I want degrees to divide out. I want radians to appear, so I'll write rad. And the conversion factor then is 180 degrees in the bottom, pi in the top. And now, if I want to convert this, I want pi visible. If you can leave pi visible in your angle, it's desirable because pi is an irrational number, and we don't have to round. So here's what we would do on our calculator if it wasn't so easy. We would just hit 90 divided by 180, and of course it gives us a decimal. We know that's 1/2, but how would you otherwise convert a decimal to a fraction on your calculator? Math, enter, enter. Math 1, 1. Math, enter, enter. So there's the math button. I hit it, it's in red, and then you hit enter, enter, and boom, it's 1/2. So this becomes pi halves. 1/2 times pi is pi over 2. We knew that. All right, before we start, what is 180 in terms of pi radians? It's just pi, right? 180 is pi. So let's verify. 180 degrees over 1 times, we want degrees to divide out, so we put it in the bottom. We want rads to appear. The conversion factor is pi over 180, and we don't need a calculator for this. What's 180 over 180? What's 180 over 180? 1. 1 times pi is pi. So there you go. Let's verify 270. Of course, we memorized it already. What's 270 in terms of pi? 3 pi halves, which is 1.5 pi. Okay, we know that. Let's verify. 270 degrees over 1 times degrees divide out. Rads appear. That's pi over 180. And we leave pi visible, so on our calculator, we'll just go 270 divided by 180. We hit enter, and you get a decimal. And how do we convert the decimal back to a fraction? Math, enter, enter. Come on in, math. Math, enter, enter. Come on in, math. Enter, enter, math. Come on in. I don't know. I have to say that every time I say math, enter, enter. I cannot say, come on in, math. I just have to say it. It's the dad in me. All right, and then 360, of course, is what? 2 pi. And if we verify, we get 360 over 1 times degrees dividing out, rads appearing. It's pi over 180. We don't need a calculator for this because what's 360 divided by 180? 2, and we get 2 pi or 2 pi rads. Now, very quickly here, let's review this. I gave you what these angles are. We're going to define it again later on, but the sooner you get it, the better. What do we call those angles that land on the x and y axis? They're the quad. We put the emphasis on quad. They're the quadrantal angles, not quadrantal angles, but the quadrantal angles. They define the quadrants, don't they? They land on the axes. They land on the axes. They define the quadrants. So you need to know those. You need to have the conversions memorized, which I think you already do. You already do. All right, now 60. 60 should be what? A little bit more than 1 radian or a little bit less than 1 radian? Ah, a little bit more than 1 radian. Because we already said 1 radian is about what? 57. Now be careful. We're gonna have a radian so permanently associated with pi. When I say a radian, pi is gonna jump into your head. So if I say what's the measure of 1 radian, most people will say pi. But pi is not the measure of 1 radian, is it? Pi is the measure of 3.14 radians. 1 radian is one length of the radius, which is about 57 degrees. So 60 degrees should be a little bit bigger than pi. How much bigger than pi? Let's figure it out. 60 degrees over 1 times degrees in the bottom, rads in the top, pi over 180. Now all we got to do is use the calculator. What's 60 divided by 180? It's 1/3, yeah. So 0.33333. Let's do it again. My calculator froze. 60 divided by 180 is 0.333. How do we convert that to a fraction? Math, enter, enter. You get 1/3. So I get 1/3 times pi is pi thirds. And of course, what's 1/3 times pi? Is it a little bit more than 1 radian? Yes, it's about 1.047 rads. Now, which version do we prefer? 1.047 or pi thirds? We prefer pi thirds because pi is what type of number? Irrational. It's a never-ending decimal. There are computers right now that are calculating the decimal digits in pi, and they have been for years. You could buy a book. In fact, I think Miss Smith's son bought her a gag gift for Christmas one year, and it's like a 300-page book, and all it is the published decimal digits in pi up to the publishing of that book. And there's still more being calculated right now. They actually have tournaments where people memorize the decimal digits of pi in the right sequence, and they show up to the tournaments and they recite the decimal digits in pi in order, and someone sits there with a book on the other end making sure they're saying the right number. Now, what do you think the world record is for decimal digits in pi being recitated? You think 500 is the record? Hey Siri, what's the world record for decimal digits of pi memorized?
What? 9 hours and 9.5 hours.
You thought I was joking, didn't you? You thought I was joking. No. They have tournaments where people memorize the digits. They show up on a Saturday morning and someone has the book and they just make sure they're saying the right number in the right seat. I only have 3.14159. That's it for me.
What if they like messed up one?
Then they lose.
I know, but
Oh, what if the publisher messed up a number?
The book didn't realize, like, oh.
I'll tell you something funny. It's funny you mentioned that. What if they memorize it wrong? Howard Aiken, he was a brilliant mathematician in the early 20th century. He was brilliant. He had a steel trap mind. He had a book that had the decimal digits in pi, but there was one number wrong somewhere around, let's say, decimal digit 2000, and he memorized it. And he later realized that he memorized the wrong number in that slot because the publisher said, oops, here is the correct number that should go there. We made a mistake. And then they said, this is funny. This is how his steel trap mind worked. They said after he memorized the right number, when people asked him to recite the decimal digits, when he got to that point in the recitation, he would pause in his recitation upward of 2 to 3 seconds while his brain had to physically switch out what he previously had memorized for what he had to now memorize. Can you imagine him saying the decimal digits 3.14159 and then having to pause for 2 to 3 seconds to manually switch out the number?
How do you know? How many do you know?
3.1415926. I only know 7. Is it 5? 3.1415926. That's all. I know 7. 7's enough for me. Is the next one 5? Okay, so you know more than I do. How does that make you feel? Superior, you should say. Yeah. So what's the record? 70 freaking thousand digits. How does that even work?
That's worse than the Tetris.
And it takes, yeah, it is. And it takes 9.5 hours to recite it. Oh my gosh. Okay.
1, 5, 9, 2, 6, 5.
All right, so let's keep going here. Let's keep converting. If 60 degrees is pi thirds, what should 30 degrees be? Pi 6, because that's half of pi thirds, right? Let's verify. Let's do the conversion. 30 degrees over 1 times, it should be pi radians over 180 degrees. Notice in all of these problems, we're using the same conversion factor, aren't we? Pi rads over 180. So I go to the calculator. How did I lose it again? Oh, and I do 30 divided by 180. And then how do I convert 0.166667 back to a fraction? Math, enter, enter. Come on in, math. So 1/6 times pi is pi 6 radians. All right, you're going to have to memorize these, so you might want to memorize them now. What's pi thirds in radians? I'm sorry. What's pi thirds in degrees? 60 degrees. And what's 60 degrees in radians? Pi thirds. All right. What's 30 degrees in radians? Pi 6. And what's pi 6 in degrees? 30. Okay. Now, let's keep going. You don't have to memorize G, but it's nice to know. If 15 is half of 30, then what's half of pi 6? Pi 12. Okay? Pi 12. Do we need to convert it manually again, or do you got the conversion factor down? You got it. Okay. How about 45? It's pi fourths. You can either say it's 3 pi 12ths, 15 plus 15 plus 15, or you can actually convert it. 45 degrees over 1 times pi rads over 180 degrees. The degrees divide out, and you get 45 divided by 180, and then you hit math, enter, enter, and you get a fourth of pi, which is pi fourths. So what's 45 degrees in radians? Pi fourths. And what's pi fourths in degrees? 45 degrees. Okay. The ones that you have to memorize are the 30, the 45, and the 60. Okay? Along with all the quadrantal angles. 60 is pi thirds. We'll write it right there. Okay? You should memorize those. Now, the ones that you don't have to memorize are the 15, which you can easily get, and then this one. You don't have to memorize this one. How would I convert negative 175.4 degrees to radians? This is what you're going to have to do on your quiz tomorrow. All I got to do is multiply that by what? No. Again, here's what you do. If you put it over 1, you have degrees in the top. You want degrees to be in the bottom so it divides out. The units that you want to appear or the description that you want to appear goes in the numerator. And now you fill it in. Pi radians is 180 degrees. Now the degrubbles divide out and we're left with radians. Is that what we want? Yes. Now all I got to do, since I want to leave pi visible in my answer, pi is already waiting in the final answer, is we type in negative 175.4 divided by 180. And how do I convert that decimal to a fraction? Math, enter, enter. And look at this. It's negative 877 pi 900. You just add pi to the numerator. Y'all can handle that, right?
Does the negative mess up anything?
Nope. No. It's still a clockwise rotation. It's just in radians instead of degrees. Yeah. All right. Now, look at this one. 5 pi fourths. Is that in radians? No. How do we know it's not in radians? It has the degrubble. So this problem illustrates how important it is for you to have the degrubble when you're talking about degrees, and why you'll lose points if you don't have the degrubble when you're talking about degrees, because we have this other unit of measure now called a radian that has no units. And if you leave the degrubble off, we and everyone are going to assume we're talking about what? If there are no units shown, we're going to assume we're talking about radians. Okay, so now I'm going to convert this. So here we go. I'm going to multiply. I'm going to multiply by pi radians over 180 degrees. Now, remember, it's nice to leave pi visible here. The pi's don't divide out, do they? But what's pi times pi? Pi squared. So if we can leave pi visible, we want to do that because pi is what type of number? Irrational, bless you. And if you'd rather write out the decimal digits, bless you, maybe I should make you go to 70,000. Huh? From memory. So now we type in the numbers. Okay? So we're going to go 5 divided by 4 divided by 180. That's how you type it in. If you're dividing by 4 and then dividing by 180, you type it in like that. Divided by 4, divided by 180. And how do I convert that back to a fraction? Math, enter, enter. And I get 1/144th. So that's going to be pi squared over 144 radians. Again, I will reiterate. If it's possible to have pi visible in your final radian answer, we want to leave pi visible in our final radian answer.
Can you simplify that? Because they're both square root. Like,
What?
the square root of pi is pi.
Correct, but we're not taking the square root. We're multiplying.
Yeah, no, but you could like simplify it.
How? How would you simplify pi squared?
Pi 12 the same as pi squared.
Oh, you want to write it like this: pi 12th quantity squared?
Yeah.
Oh, you can do that. That's fine. But which answer looks simpler to me? How are you going to know what I'm thinking, right? Which answer looks simpler to me? The top one, because there's no parentheses. But yeah, you can write it as pi 12th quantity squared. That's fine. I have no argument with that. They're both perfect squares, is what you think. But what we can't do, we can't just say that it's equal to pi 12ths, can we? We can't just take the square root of something without changing its value. Now, if it were an equation and we had two sides of an equation, we could take the square root of both sides as long as we do plus or minus, and that's legal. But when we're dealing with an expression, the square root of a number is not the same as the number, is it? Unless you're talking about 1 or 0. What's the square root of 25? 5. Would you rather have $25 or the square root of $25? I'd rather have $25, yeah. Especially in today's economy, right? Yeah. Okay. Let's see if we can convert the other way now. What if I start with radians? Can I convert to degrees?
Yes.
Yes. Now, look at this. I'm going to write rads up there so that I have something to divide out. I'm going to have rads down here and now degrees in the top. What's the conversion factor now? Is it still pi over 180?
180 over pi.
It's 180 over pi. So the rads divide out, the descriptions divide out, and I have units of degrees. Now, notice what else divides out. Holy yes. The pi's divide out. So now I just multiply 5 times 180 divided by 4, and I get 225 degrees. You're going to end up memorizing that 5 pi fourths is 225. No, because it's already a fraction. Yeah, if it's already a fraction, you don't want to make a complex fraction out of it. Just like 11 pi 6. I don't want to put it over 1 because it's already a fraction. So I'll just extend this and put rads in the numerator is what I'm doing. Yeah, because it wasn't a fraction. Oh no, I didn't put it over 1. No. Because it was already a fraction, I just multiplied by the conversion factor. Yeah. All right, 11 pi 6. Let's see if we can get to this example. I'm going to multiply again by 180 degrees over pi rads. Not just the rads divides out, but so do the pi. And so now we're left with 11 times 180 divided by 6. And we get 330 degrees. That's another one that you're going to end up memorizing. 11 pi 6 is 330 degrees. Those are equivalent angles right there. All right, 2 pi thirds rads. I'm going to multiply by 180 degrees over pi rads. The rads divide out, the pi's divide out, and I'm left with 2 times 180 divided by 3, which is 120 degrees. That's another one you're going to end up memorizing. But for now, we'll just convert it. Those are equivalent. The next two you're not going to have to memorize, okay? But we'll convert them anyway. We got rads in the top, so rads in the bottom, degrees up there. So I get 180 over pi. The pi's divide out, so we get 7 times 180 divided by 5. Boom. You get 252 degrees. So 252 degrees is the same as 7 5/5 radians. Now notice the last one. Is there any pi visible in the last one? No. It's just 1.346 lengths of the radius. It doesn't have to have pi visible. So I'm going to go ahead and write rads, and because it's not a fraction, I'll put it over 1. And I'll multiply by, again, rads in the bottom, degrees in the top. So I'll multiply by 180 over pi. Now, in this case, because our answer is going to be in degrees, we'll go ahead and multiply pi in. Unless it's a radian angle, we don't want to leave pi visible. So I'll do 1.346 times 180, and now I'll divide by pi, and I get 77.120 degrees. Okay. We only want to leave pi visible if it's an angle in radians. All right, and that takes us through example 9. We're done for today.